Let's see, I've got the audio working, video is working, and this video is going to be a discussion on completing the cube, geometric implications, and how we can use what we figure out here in our classrooms. I think I did it for the department a couple of weeks ago, and I want to make sure everybody got to their classes on time, so I kind of rushed through it. So I'm hoping to really talk about this in more detail and at a slower pace. All right, so we'll have at it. I put some things on the board. I hope that I do justice to this topic, and we'll see. All right, so looking at y equals x cubed and thinking about volume being the side cubed in terms of geometric representations. And we'll have sine volume, minus 27, -3 times -3 times -3. And then smaller cube, -2 times -2 times -2, so on and so forth, until we get over to the right side with a positive volume, 3 times 3 times 3, 27. And I'm just capturing a little bit of data here. And we can see our signature cubic and really want to talk about how things are changing. So we're going up 19 units from -27 to -8. So we can kind of draw the secant between the two data points. And we can talk about -2 gets me -8 and -3 gets me -27. And, we have an average rate of change of 19 to 1 units. X is changed by 1, Y values change by going up 19. And we can do that straight across from each geometric shape. We will go up 19, we go up 7, we go up 1. Then from 0, we go up 1 again, and then up 7 and up 19. And I think we can start to get a little feeling for rates of change, going up, but not as quickly, certainly not as quickly. And then it seems like the least amount of change in the Y values is occurring at x equals 0. 0 times 0 times 0 is 0. And 1/10 times 1/10 times 1/10 is 1,000th. And not changing much there. Whereas a little bit of change over here, we get significant volume change compared to here. Okay, so it seems to me that the point of inflection, concave down to concave up, occurs at that moment where things are changing least quickly for a positive cubic. Now, least could be a negative number like -20. That's smaller than -19. All right, the magnitude's bigger, but we're talking about minimizing rate of change. That's kind of the topic at the moment. So let's take a peek at a different cubic. Ones with roots 0, 2, and 10. And we'll just draw the cubic and get a sense that there's a point of inflection at some x value. The question is, why is it there? What's going on? All right, we can also see that the largest negative slope is occurring here, right? Increasing, 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 slope is 0. And then the tangents are more and more negative. Most negative tangent right here for slope. And then we start to swing it around again to positive slope tangents. And that one seems to be the most important slope. The question is why? Why is that happening? And it turns out it's geometric in nature. If we were to construct a cube with roots at 0, 2, and 10, I believe I said. Well, excuse my art skills here, but x, something slightly smaller, something much smaller for a height. We got our length, our width, and our height. And students should, coming out of Algebra 1 or Algebra 2, be able to certainly write the equation based on the zeros. And if we plotted that, again, we plotted it over here a minute ago. See if we can get that picture one last time over here. We plotted, roots at, we can see that 0, 2, and 10. 0, 2, and 10. But there's something really interesting going on at that x. And it turns out it's the average of the roots. The x value of the point of inflection is the average of the roots, because what we're going to try to do is redraw this so that it's a perfect cube. And that means you got to even off the sides. And so we've got some dimensions to work with. And if we add them up and divide by 3, by golly, we get the x value of this point of inflection was actually at 4. Now, I think it would be helpful if we actually started teaching y equals ax plus b instead of mx plus b, and y equals ax squared plus bx plus c. And let's make sure that you can see this. Yep. And y equals ax cubed plus bx squared plus cx plus d. Standardize our approach, and we would find that minus b over 2a is the average of the roots. Minus b over a is the average of the roots. There's only one. This is where a linear function changes signs from positive to negative or vice versa, from negative to positive, right? Unless it's a constant, y equals, right? Then it wouldn't have roots. But minus b over a tells us information. Minus b over 2a, sure. I mean, if you just factor ax squared plus bx, you got a root at 0, you got a root at minus b over a. And what's right in the middle? Minus b over 2a. Turns out minus b over 3a is the average of the roots of a cubic. And so if I took that average and it's 4, then I could redraw the cubic as a perfect cube. X minus 4 times x minus 4 times x minus 4. And I did it on the side over here. I multiplied it out and I got that cubic. X cubed minus 12x squared. And if all I did was multiply x minus 4 cubed, right, which I did all of it, we get those first two terms. Which happens to be the same first two terms if I had multiplied x times x minus 2 times x minus 10. That gets me the same first two terms, which means I could rewrite this as x minus 4 cubed, and I'd get those two terms, and then I'd get a lot of algebra after it, which I could reconfigure using some conversion techniques, right? And it turns out that if you want to see that process, then you can look at the putting cubics in graphing form. It's on my YouTube channel, right? And so I did that in another video, but you could have also done it with some calculus. You could have done the first and second derivatives. Second derivative changes signs at 4. So we know we got our concave down, concave up intervals that we'd stress at the calculus level. But if you put 4 back into the quadratic, you'll find that you're at the minimum. You get a value of negative 28, which means that if I take the slope of the tangent and then build off of that point of inflection, which 4, negative 48, plugging 4 into the original, you get negative 48 out. Some nice little math there. There's a 3-to-1 ratio, quadratic to cubic term. That's always there at the point of inflection, that 3-to-1. In the quadratic, it's a 2-to-1 ratio. So if you put a 4 in here, you get 48. So you know that without looking, this is going to be minus 96. It's a 2-to-1 ratio, but you go check it out. And then you add 20. That gets us our slope at the point of inflection, minus 28. And so if you put this all together and did it out, you'd actually get x cubed minus 12x squared plus 20x. So that's the graphing form. This is the graphing form for a cubic. The x minus 4 cubed, right back to the beginning of this little lecture. That's where this cubic is not changing, right? So let's get the linear component out of there, right? So add 4, no volume, right? No volume, very little change in the y values, in the volume values. And if you draw another linear component, then the rate of change is going to become the linear rate of change. All right, so if you're looking at f prime and g prime, right? If f prime, the cubic, is not changing, then all of the change is coming from the linear component. And we can see that over here in the original again, the original graph. Let's see, where am I? Here. Yep, okay, get my leg out of the way, right? So this has got that no volume cube there change, and there's the linear. And so you can start to see the trajectory here a little bit. And there's ways to find the x values of those max and mins with a little bit of, I forget if I did it algebraically. Anyway, it's h plus the square root of minus m over a. The a term is 1 in this case. I don't know where I wrote it, but the x minus 4, right, it's cubed. It's got a 1 for a coefficient, so that's what the a term is. The slope in this case is minus 48, so we'd have to do minus 48 here. And h is 4. So it kind of looks a little bit like the quadratic formula. And so that's a 1. And so that would be this x value. The one down here would be 4 minus the square root of 48 over 1. So that's that x value. So you can find those without calculus. What else did I want to talk about here? What points have I missed? Well, I guess the major issue here is just getting kids started sooner with concepts of rates of change and where they come from and how we analyze them. I think there's a lot of important mathematics in this. More things to talk about, but feel free to ask away. And just hoping that you can, if I missed anything that I wanted to talk about. I don't believe so. All right, so I think it's important to know minus b over 2a is the average of the roots of a quadratic, and minus b over 3a is the average of the roots of a cubic. And you can continue with minus b over 4a, minus b over 5a. You can put fourth degree polynomial expressions in functions in graphing form as well. Doesn't tell you much, but the cubic one does. The cubic one tells you a lot. And the more you go up the ladder, the more complicated the pictures become. But you can always get rid of that second term in a polynomial by taking the average of the roots. And so if we did x minus h in parentheses to the fifth, we would get rid of the fourth degree term in a polynomial. And so therefore you're writing something with fewer terms, which means you can look at the graphical expression of those two terms and try to, in your mind, configure what the graph looks like. It just gets more complicated every time you add a term. But I think the cubic lends itself nicely to graphical analyses. And being able to do it algebraically, some good algebra comes out of the conversions that allow you to write that in graphing form. My good friend Neil Shealy, someone I've been talking math with, who, you know, when he gets started is on a roll. It's hard for me to follow him, but he saw the graphing form for the cubic and then realized that you can find the roots pretty easily using some trig and some higher level mathematics. That was hard for me to follow because I don't have experience with it. But he took this and ran with it. And I'm not sure if what he did is out there already or if he just figured something out on the fly. I don't know, but I'll have to ask him the next time I talk to him. And so feel free to ask any questions about this process. I showed kind of what I wanted to show, but I'm sure there's all kinds of other things that come out of this. I noticed that when I multiplied out x minus 4 cubed, for instance, 12, 48, 64, there's some interesting numbers there. There's some real interesting numbers. So I'm sure that actually getting into the geometry of the perfect cube in more detail would probably give all of us a chance to see where these numbers come from. There's a pattern there. Pretty sure there's a pattern there. I haven't thought about that much, but that's the kind of thing that you can dive into and have fun exploring. So hope this helps a little bit, maybe deepen understanding in some areas. And I think we should always be doing that as much as we can because we have the responsibility of explaining things to other people. Okay, so toodaloo.